Welcome to this module of the ZK Whiteboard sessions. I am Nico, I'll be today's host, and today I'm super happy to have a return guest, Jim from Irreducible.
Hi, I'm Jim. I'm the CTO at Irreducible, and I'm very excited to be here.
Great. What are we talking about today, Jim?
Today, we're going to talk about high-performance engineering for SNARKs and how we can make the best use of our technology to implement these protocols very efficiently.
Nice. So what does that entail? Like, what are the themes that we're going to go through?
This is really a story about how we identify bottlenecks, decide whether they're computational bottlenecks or memory bottlenecks, and break through them by using software engineering, hardware engineering techniques. And we're really going to pursue the story of how do we exploit parallelism to distribute our work over multiple resources to bring down the time it takes to produce a proof.
Cool. Shall we get started?
Let's get started. So we need to recall a basic SNARK protocol. So in this session, I'm going to focus on hash-based SNARKs, if that's okay, or hash-based SNARKs, for example, STARKs. Yeah. And we're going to have a little toy example of a STARK over the baby bear field. So we, I think, spoke in our last module about small field STARKs. So the baby bear field is a 32-bit prime number. And it's become very popular for STARKs because it's compatible with the NTT. And we'll have a STARK protocol where we have a table that has 3 columns. And we want to evaluate a constraint over it. For example, a times b minus c equals 0. And we want this to be true at all rows in our trace. And if we recall, the major steps that we're going to do in a STARK are, number 1, witness generation. So this is when we arithmetize the problem and fill in the trace matrix. Number 2, we need to commit the trace. And in a hash-based SNARK, this is going to involve a number theoretic transform for error correcting code, and also a Merkle tree. Yeah. The third step is constraint evaluation. This is when we take this expression and evaluate it over every row. And the last step is the PCS opening. Yeah. And we'll be a little non-specific about the PCS. We can imagine this being either Fry or something like Lehero. Mm-hmm. And as a rough sense of like how costly these different operations are, if you run Plonky 3 for a Poseidon, every different constraint system might have a different profile, but we could roughly think about this as being 10% of the overall time. This as being 30%, 30%, 10%, and 20%. Why is this? Number theoretic transforms are asymptotically more expensive. They're super linear, whereas these steps are both linear. Hashing is just a sort of different type of operation, and it's more expensive. And our PCS opening is going to be more expensive than constraint evaluation because we're doing extension field operations instead of small field operations.
Makes sense. Just to jog my memory, entity here is because we're doing this encoding, right, of whatever is there. And then constraint eval is when we check everything is indeed 0.
Exactly. We're also actually using the NTT for the constraint evaluation because this is a polynomial multiplication that has to happen over an extended domain.
Makes sense.
Okay. So how do we go about making a STARK that's doing this operation faster? Mm-hmm. Well, first thing we want to do is just minimize the number of instruction cycles that it's going to take to do this. So what we'll see is when you look at all of this, there's really 3 operations that we care about. Base field multiplications of baby bear elements, yep. Extension field multiplications of baby bear 128-bit extension elements, and the hashing, which is a sort of special thing. So you'll remember that even though the entries in our trace are 32-bit elements, we need to use like baby bear degree 4 extension elements, which are basically vectors of 4 baby bear elements, and there's a multiplication algorithm associated with them.
And here viewers can refer back to your previous module, right?
Exactly. So in order to just reduce the number of instruction cycles in a CPU implementation, we'll use standard techniques like turning on compiler optimizations, inlining, looking at assembly. But we'll quickly find that we want to increase our field multiplication throughput, and there's not really a way to do that by reducing the number of instruction cycles. So how are we going to increase multiplication throughput without reducing the number of cycles? We need to exploit parallelism. So
one instruction is going to do more multiplications than it did before.
Exactly.
Okay.
So different CPU architectures have different instructions, but this is called SIMD parallelism.
What does that stand for?
SIMD is single instruction, multiple data. So one instruction is going to operate on a 128-bit register. We'll think about ARM Neon as giving 128-bit operations, and your 128-bit register is going to get split into 4 lanes. Each one is a separate baby bear element. And so on.
Yeah.
And now we'll do the same number of instruction cycles to, say, multiply baby bear elements. So if we have 2 of these registers, we can multiply them, but every time we do that sequence of instructions, it's going to multiply all 4 of these in parallel. Okay. These would be called lanes. So we're going to use these SIMD instructions to exploit parallelism, and where does this help us in our SNARK?
Yeah, so I guess we said NTT was some multiplications,
so
constraint eval, yeah.
Yeah, exactly. There's field multiplications happening really in all the steps except for hashing.
Yeah.
We'll get back to the NTT because this is a bit of a trickier case. So let's start with constraint evaluation. So what does this mean again? It means we have many rows. We could think about having, several million rows or so, and we want to evaluate this operation on each row. This looks like what we'll call an embarrassingly parallel operation. You don't need to do any work to find the parallelism. It's just you're doing a separate thing for each row.
Yeah.
So how would we lay out a SIMD operation for this? We're going to treat our columns as vectors of SIMD registers. So we might put 4 elements here, sort of column-wise. So
this, I see.
Into one of these, this will be 128 bits. We'll do that for A, B, and C.
Yeah.
And then if we had 1 million rows, now we need to do 1 million divided by 4 multiplications on these SIMD registers. So this is going to reduce the total number of cycles we need to compute the operation over the whole matrix because we're exploiting parallelism.
Nice.
There are some interesting considerations that happen when you have to engineer one of these systems. One is that these registers are more efficient to use if they're stored at memory addresses that are aligned with the size of the register, meaning in the program, the memory pointer to the beginning of A should have its bottom, it should be a multiple of 128. It should have its bottom 7 bits cleared, which is not something that a normal memory allocator will do for you unless you pay specific attention to this. So alignment is one consideration. Another interesting engineering challenge is that different CPU architectures have different SIMD instructions. So we'll normally need to hide these behind compiler feature flags and specifically manage that, but that's all going to be handled in the abstraction of our field library generally.
Or have a library that's specific to one specific processor, right?
Yeah, exactly.
Okay, I see.
So where else can we apply SIMD optimizations? We said constraint evaluation is an easy place. Our PCS opening is another interesting case where we have parallel operations, but they're overextension field elements.
Okay.
So what does this mean? We have, I was showing up here that we have these baby bear quartic extension elements. So I'm going to sort of write this as so these are the 4 baby bear elements that make up the limbs of one quartic extension element.
Cool.
So how do you think we should represent this in memory?
I mean, can we plug them directly into our lanes?
Yeah, that seems like a very natural thing to do. We have these 128-bit registers. We can put one limb per lane. Actually, that's going to generally harm our ability to do parallel operations.
Okay.
If we were to do this, we need to take a bunch of cross terms when we multiply 2 elements, and that's going to require us to use SIMD shuffle instructions.
Right.
This is possible, but it's just adding more cycles for something where we want to maximize our throughput.
Just to be sure, this is because, so addition would be limb by limb, but multiplication has like cross-limb things happening, right?
Exactly.
I see.
If I recall correctly, it's something like 17 different cross products of limbs in order to do a baby bear quartic extension multiplication with reductions. So instead, we could actually think about using 4 SIMD registers to represent many different baby bear extension elements. So think about having 4 quartic extension elements and laying them out where all of the A limbs from one live in one SIMD register, all the B limbs from this small element live in another SIMD register, here's another SIMD register, and here's another SIMD register. And when we want to multiply 2 of these elements together, it's easy to take the cross terms because we can take this register times, if we wanted to multiply this by, E, F, G, and H, it's sort of easy to take the cross term of C times F and C times G, and we're just doing 4 extension field multiplications at a time. So we are actually able to, even though our PCS opening phase is doing extension field multiplications, if we choose our memory representation in a clever way, we can get sort of embarrassingly parallel speed up as well using SIMD.
Okay. Is there an issue where here we've aligned our memory in a certain way to fit, ABC here? And do we need a different alignment to be working on extension fields?
That's a great question. The alignment doesn't need to change because we care about alignment for loading data from memory into a register, and that just requires the alignment of the register size. Okay. But it's a common abstraction to have packed field elements or objects that represent a fixed length vector of field elements. And in this case, if we had the amount of data that it takes to store a packed extension field element is equal to the number of lanes times the extension field. So it's bigger than the amount of data to store like one packed baby bear element, for example. Okay. We can go further with SIMD parallelism. So it actually makes sense to often implement SIMD hash functions. If we're building a Merkle tree, then you are performing many separate hash operations in parallel, so you could use SIMD lanes to store, different portions.
Inputs to the hash every time? Okay.
Yeah, different words in your hash. Basically, one SIMD register, each lane is performing a different hash function at the same time. And then we need to talk about the NTT. So let me erase this part. So how does the NTT algorithm work? You basically have let's say a vector of elements that you want to NTT. This will be something like 256 elements. And we generally write this, or we can visualize this as this butterfly network. I don't know if we've talked about this before, but you're going to take to begin with, every pair of adjacent elements and do an operation where something like this, and y is going to be computed as a linear combination of x and w, and z is going to be a linear combination of x and w. The memory layout of this is something like this, where we take pairs of adjacent elements, and then on the next layer, we're going to take kind of larger strides.
I see. Yeah.
And then on the last layer, we're going to take larger strides than that. So we can parallelize through each layer, but that isn't the easiest parallelism to exploit.
Okay.
So there's another way of looking at the NTT, which makes the parallelism, I think, more apparent, which is if we have this vector, we're going to first reshape this into a matrix. Let's call it 16 elements by 16 elements. There's an algorithm called Bailey's NTT, or the 4-step NTT, which is we are going to take our matrix. The first thing we're going to do is perform, well, let's say we're going to transpose it. We'll do NTTs independently on each row.
Each row, okay.
And so now we have 16 parallel NTTs that we can do across each row. We have to transpose it back. And then we'll complete it by doing 16 row-wise NTTs again. They're actually NTTs onto different cosets in the second phase, but
it still holds that we get to work row-wise.
We get to work row-wise. We get to introduce parallelism by reshaping into a matrix at the cost of having to do these two transpositions. So these become the only sort of bottleneck in the NTT where we don't get to parallelize as much as we might want to.
Right.
So at this point, we've basically talked about everything except witness generation, which we'll hold off on, and shown how there exists parallelism in all of these operations that we can take advantage of. And the first way we're going to do that is with SIMD instructions. So how do you think we're going to go even faster than just using these SIMD operations?
All right. So at this point, we have one processor. We're using as few instructions as we can, and we're making sure that each instruction has sort of as much data as I can treat.
Exactly.
Okay. So do we have more processors?
We do. Modern CPUs have many different cores, and you program them using many execution threads that will get scheduled onto different cores. So let me clear some space. So a modern, say, quad-core processor means the CPU...
I guess it's in the name, right?
Has quad exactly core. 4 cores, yeah. Right? So
this is our CPU, and
this is our CPU, and we're going to flesh out this diagram in a little bit. But we have these different processing units. We've already shown that the algorithms we want to do have parallelism that we can exploit. So if we took our big table, we can just split it into, say, 4 segments and do the polynomial evaluation for the first quarter of it on one CPU, on one core. The next core would handle the second one, the next segment, and so on.
Yeah. Do we then need to do some work to put everything back together?
Well, the awesome thing is they're all going to have shared access to main memory. So nice. Here's our memory. And in on a chip, you have the main memory, which is like DDR, but then every core has a local cache. So you may have heard about different cache types. The smallest and most local one is called the L1 cache.
Not the layer 1 blockchain.
Right. The L1 cache is the fastest to access. So anytime a core needs to access memory, it will bring it into its local cache, operate on it, and then write it back. So when we are operating on multiple segments of the same table, you only really need to transfer each word in the segment to the cache once if we're only using it once. So for something like constraint evaluation, which is a sort of streaming pass, which is you're doing one pass over the table, this has a really efficient memory access pattern. What about something like the NTT, where we had this transpose, though? So what does it mean to take a big block of memory that's stored in main memory and then read, different strides of it or different columns of it into different CPUs? We're going to start seeing a memory bottleneck. So this means that as we increase the number of cores, roughly all of the steps except for the NTT should speed up pretty much proportionally to the number of cores we have until we hit a memory bottleneck. And the first place that's going to happen is the transpose that's happening in our NTT, or however we choose to do strided accesses. Where does this come from and what can we do about it? Well, we have a memory hierarchy in a CPU, meaning we have layers of caching, we have memory, and then another thing that every CPU has is called a translation look-aside buffer, the TLB. This is when you need to resolve an address that you have in your program to where it lives in physical memory. And this is basically another type of cache that if you have a cache miss on any of these different caches, it's going to slow you down. So that's why you want all of the memory accesses to be very sequential and predictable, and an access pattern like the transpose in an NTT is going to violate that.
I see.
We'll get back to like what we can do. Well, ultimately, what can we do about memory bottlenecks? Well, we can get better technology for memory. We can find memory that instead of using GDDR6, we'll use GDDR7 or like the new generation.
So do we mean it's just faster to transfer between a core to the memory?
Or generally we'll be talking about higher bandwidth memories. So we care somewhat less about the latency of accessing memory than the bandwidth of loading a large segment of main memory into a cache. Putting aside the question of memory bottlenecks, if we're still compute bound, what can we do? If we want to lower we can't scale up the number of CPU cores infinitely without paying a lot more for it. So how can we get more compute?
So we can't have more cores per CPU, can have more CPUs?
Yes, exactly. You could have more CPUs and, well, actually, we can have more cores, but we need to move to a different type of hardware, which is a GPU. So now we're going to go from running operations on a CPU to a GPU. This stands for graphics processing unit, but they've really come a long way since the days of being only used for graphics. You probably know that they're being used widely in AI because, and what do they do? Well, they're a different processor type that just has a lot of compute for parallel operations, and they're less flexible. But if you really need high throughput of low-level arithmetic operations like integer multiplications and floating point multiplications, a GPU is specially designed for that. So to give you some rough numbers, if you look at cloud available compute resources on AWS, you could get an ARM CPU instance, which would be something like a C8G ARM instance with 16 cores for roughly the same price as a G6 instance on AWS, which has an NVIDIA L4 And this thing has 6,144 CUDA cores.
Wow. So can we think of those CUDA cores as almost equivalent to like a CPU core?
Each CUDA core is going to be less powerful and more limited in its functionality, but we have so many more of them that the overall the overall throughput of arithmetic operations like integer multiplication is going to be a lot higher for the same price point.
So if we were to draw like something similar to this diagram for the GPU,
as I recall, for an L4, you have what they called many different SMs. I think those are simultaneous multiprocessors. So you have something like 48 SMs in a grid.
Yeah.
And each one has many cores within them.
Many to add up to
many
this number, I
cores,
guess.
yes.
Yeah. Okay, I see.
So this is what our GPU will look like. And in many other regards, it actually looks a lot like a CPU. You have a global memory. This might have a different underlying technology for accessing global memory, but you have a global memory, and each SM has a local memory, which can be used either as a cache or in a way that you have more manual control over. So what are some of the other, basically, is this a free speed up?
Yes.
Not really. We actually need to put in quite a lot of work to figure out how to use this device efficiently. So the first thing is, it's not as flexible as a CPU instruction set. You can't just write Rust code and compile it and run it on a GPU without doing something special. And so we need a library that's going to help us access the GPU resources. For every hardware vendor is going to have some...
They have their own libraries?
They're going to have their own library. So most people in the space are using CUDA, which is an NVIDIA-specific compiler and toolchain technology for programming NVIDIA hardware. This allows you to write C++ code, but you need to think more carefully about how it's going to map onto the GPU hardware. And what do we need to do to run this from our Rust code? Ultimately, we need to write the C++ code and link it to our Rust library.
I see.
Without going more into the toolchain aspects, the biggest conceptual difference is that we can't deal with memory in the device in the same way that we handled regular memory pointers to our system memory. So, as I said, you have a main memory in the GPU. And in our program, we need to keep track of the fact that our table that we're actually trying to operate over does not live in a shared memory space between the GPU and the CPU. First, we need to transfer it from our motherboard. We'll call this the host. And this would be connected over a system bus to the GPU. These are two separate pieces of hardware, two separate chips, generally. We need to actually transfer data from the main memory here to the GPU. And our software, again, needs to track where in the GPU's memory space each piece of content lives, and that's more code to handle.
Is this something for the software to track or the engineer to keep in mind and write the software with that view in mind?
Absolutely both. You, as an engineer, need to be pretty thoughtful about where memory is going to live. And one thing that could help you manage that complexity is a hardware abstraction layer. So this is something that a high-performance cryptography library might have to introduce themselves, which is a software abstraction for running operations over different types of hardware.
I see. Oh, and I guess this also allows to get away with, you were saying each vendor will have its own language, like CUDA or other.
Yes, so if you also wanted to support Apple GPUs and like the Metal framework, you could write a hardware abstraction layer that makes it so that you as a cryptography engineer wouldn't need to know the details of these libraries. So what is like, how do we make the most efficient use of a GPU? There's a principle in GPU programming that what you want to do is feed the beast. You have all these really powerful processing cores, and the worst thing that could happen is that they're sitting around idling,
doing nothing,
waiting for a memory transfer to happen before they can start their work. So if we have a paradigm in which we need to transfer data from the CPU to these multiprocessing cores over a bus, which is a fairly low bandwidth link, we want to make sure that either we can generate the data in the device to begin with, that we actually can avoid the memory transfer altogether, or that while we're transferring memory, we're also working on the data that we received last. So if we have like a gigabyte of memory that we want to process in a streaming fashion, so we have a gigabyte of data here, and we want to send it to the GPU and get it back.
But our bus doesn't have like 1 gigabyte sort of bandwidth, I guess.
Yeah, or
like instantaneous.
There's some latency to doing this, and even if we had 1 gigabyte per second speed, that would take a full second to process the data. So the most naive thing we could do is send 1 gig, wait for that transfer to complete, do all the processing, and then transfer it back. And if, let's just say we can have a bandwidth of 1 gigabyte per second, then it's 1 second to transfer it, our processing time, and then 1 gigabyte back.
Definitely not feeding the beast here.
Definitely not. It's what are our processors doing while we're transferring? Absolutely nothing. So this is the concept of operation pipelining. We want to pipeline our memory transfers so that it's overlapping with processing. So as soon as we've, say, transferred the first megabyte, so we can think about this as being like time. So let's call this host to device transfer. So if this is our host to device transfer, and it's going to be this amount of time. And then on the bottom, we want to do device to host. And then in the middle, we want to compute. What we'd like to do is, as soon as we've transferred like the first megabyte, we can begin computing on this. And then as soon as we've computed the first megabyte,
we can send it back.
We can immediately start sending it back. Assuming our link is bidirectional and we can send data in both directions. So what this lets us do is for essentially the amount of time it just takes to transfer the data, as assuming that data transfer is in fact our bottleneck here, we don't need to wait for the compute to happen in the middle, and we can overlap the transfer on the way to the device and the way back. And in fact, even we can take this further. If our computation involves multiple steps, it might make sense to partition the processors here so that like the first half of the processors are doing the first phase of it. They transfer data to memory, and then the second like half of our processing cores can pick up.
So this can also be pipelined, essentially.
This can be pipelined. Where might that come into play? Well, for commitment, we need to do these number theoretic transforms and then Merkle hashing. And if we structure things in the right way, we could potentially begin our Merkle hashing while we're still doing part of the NTT.
As soon as part of this becomes available, hash it.
Exactly.
Keep going. Nice. So one question that comes to mind for me is, could we have been doing this pipelining without even going to GPUs, right? Could we have been doing this in the first place with our CPUs?
Yeah, that's a really interesting question. We need to think about what pipelining is giving us. So what pipelining lets us do is put our compute resources to work if they would otherwise be blocked on something. So I gave the sort of example here of pipelining data transfers with compute, because actually the bandwidth on this bus link is a different resource from our compute resources. If we have algorithms like this and this, which are embarrassingly parallel, they're not really getting blocked, they're just compute bound, then we can put all of our cores to work and it's not going to help us too much. But in other settings, we can be thinking about pipelining if we're doing signal processing streaming applications, or if we're blocked on disk I/O or anything like that.
I see. Or blocked on waiting for one step to finish to the next, right?
Exactly. Yeah.
Actually, with that in mind, are there like specific SNARKs that have a structure which allow pipelining from one step to the next? Or are there SNARKs that are really bad at this, for example?
So a really interesting resource in SNARK design is interaction. This idea of taking an interactive protocol where the verifier sampling randomness allows them to avoid more work. So a STARK is an interactive protocol, but there's very few rounds of interaction, actually. We need to wait for the commitment before we proceed to this phase, and then we might have some interaction rounds in our PCS opening. But there are other SNARK designs, like sumcheck-based protocols or protocols based on GKR, that may have overall less computation, but use more interaction. And what does that look like for a high compute environment? The GPU multiprocessors might be waiting for the last round of interaction to complete, for the verifier to sample new randomness to get started again.
Right.
So there's an interesting design space of understanding the compute, like how compute bound our problem is. And if it is, we might introduce more interaction. But if that's not a problem, then we might reduce interaction in order to feed the beast.
I see. And so the reason we have to wait for one round of interaction to finish before doing the next is because we usually do fiat shamir and we need to commit or hash everything that's happened in one step to get the verifier challenge, right?
Exactly.
Okay. And so concretely, you were giving examples like something that uses the sumcheck protocol will use a lot more interaction than what we have here, which is just interaction, I think, here, right?
Yes.
Okay.
So here we showed a new degree of parallelism. We took a new hardware platform that gives us many different cores that we can operate over. And so what if we want to reduce the time to produce a proof even beyond that? Well, we're going to scale up to multiple machines.
Right.
We're going to start talking about
this whole setup multiple times.
Just, you could think about a rack in a data center with many servers, each having many GPUs connected to different PCIe links. So how do we manage that? I mean, now we're talking about SNARK proving over a cluster of servers.
How do we feed the beast?
So we have a new resource limitation in this setting, which is network bandwidth. If we have many servers and they're...
So this is the link between the servers?
This is, yeah, exactly. The network links connecting multiple servers to each other. And this, for example, becomes a big bottleneck in like AI training, where you have really advanced technology for high bandwidth data transfers within a data center so that you can distribute your training over a large cluster, but they're accessing a single large data set. In the SNARK design space, we have a really interesting way of getting around the bandwidth limitations. So maybe I can like draw a little like a rack of servers here or something. So we have, server 1 and 2, and these are actually just different boxes, and each one has a CPU
and a GPU and its own memory.
Exactly. And they're connected generally with like a top of rack switch, but they'll be connected with Ethernet or something like this. And so what can we do to avoid any sort of bandwidth bottlenecks? Well, there's an amazing thing about the SNARK setting, which is SNARKs essentially compress verification, right? That's, in fact, the entire point of a succinct proof, that you want to take some statement and compress it into something smaller. So we can exploit a sort of compute bandwidth trade-off by leveraging recursion. So if we want to compute a virtual machine computation for, if we're trying to prove 1 billion RISC-V cycles.
Yeah. So can we think of this as our computation trace with 1 billion rows, give or take some number of rows?
You could think about this as a computation trace with 1 billion rows.
Cool.
The first thing to note is the total size of that trace, if it was all put into some memory at the same amount of time, at the same point in time, would be enormous. Probably hundreds of gigabytes, or potentially more. So actually, total amount of memory might become a limitation for us as well. But using recursive techniques, what we could do is split this into, let's call it 1,000 segments. Each 1 million cycles. And instead of proving all 1 billion cycles at once, we'll first generate independent proofs for each segment of 1 million cycles. And then we will recursively aggregate them. So if let's say the working memory size to produce a proof for 1 million cycles is 16 gigabytes.
As long as each machine has 16 gigabytes, then we can do this, I guess.
Yes.
Okay.
As long as each machine has 16 gigabytes, and we're going to compress the output of the proof might be 200 kilobytes or something like this. The next thing we need to know is how costly is it to do a recursive proof that compresses 2 leaf proofs into 1.
And we want to do this because we have 1,000 proofs for, like, 1 proof per segment.
Yes.
And we want to bring it down to just 1 proof for the whole thing.
That's exactly right. We want to compress an arbitrarily large computation for any number of cycles into a single proof that's a manageable size. And we're going to do this by distributing the segments of computation over the entire cluster, and then distributing the work of recursively compressing 2 proofs into 1.
I see.
So, we can think about these being our billion cycles, and we're actually going to build, it's pretty common to just build a binary tree of proofs where this proof is going to produce a new proof blob here. And then at the end, as you said, we're going to take all of these proofs and create just our final proof.
And why are we doing this as a tree?
The reason we're doing this, so that's a great question. What else could we do? We could potentially just go through this in sequence. That would be, in literature, sort of like IVC, or incrementally verifiable computation, where you're updating a running proof. And the reason we want to do this in a tree fashion is because that allows us to have more parallelism.
Always the answer.
Always the answer. So how deep is this? Well, if we have a binary tree, it's log depth in the number of segments. So it's actually, log 2 of number of segments. And this essentially dictates our latency of computation. And also, if we think about it from a resource utilization point of view, having more proofs to produce at any given time means we get to put all of our servers to work, which means we get to put all of our GPU cores to work, and so on.
So as we move up the tree, we can free up some GPUs, some actually servers in this case.
I mean, if we're just trying to produce a single final proof for 1 billion cycles, as we get closer to the end of the tree, our servers are going to start idling, but they've done a lot of work at that point already.
Fair.
Another really interesting thing happens when we get up to the level of cluster level computing, which is we're going to run into a new bottleneck, and that's around witness generation. which is pretty much the only thing we haven't talked about as an explicit step. So we talked about how this is parallelizable, this is parallelizable. We talked about at this point 4 different ways to compute when you have enough parallelism. When you get up to the level of essentially having as many servers, many GPUs as you want, what is the sequential bottleneck? It's actually just the time to emulate the RISC-V execution and to store all of the information needed about that execution to do the parallel work of producing segment proofs.
Right. So to fill out the trace? Or it's more than that?
I think to begin with, it's to fill out the trace, but we can actually be more clever than that.
Okay.
We don't need to fill out the entire trace sequentially. What we're going to do is a sequential pre-flight execution. This is a term that RISC-0 uses and that I first learned from them. You'll do a pre-flight execution, which is a pass over the computation that is meant to be as fast as possible, but it's going to log enough data about what happens in the middle of the execution to then produce the segment witnesses in parallel.
I see.
So if we have 1,000 segments, and let's just say we snapshot the entire memory at every segment of 1,000, then we'll do a second pass over the entire execution, but in parallel, running over every segment, doing the more expensive work of filling out the trace table.
I see.
And the other thing this is going to let us do is save memory, because we can use less memory to store the snapshot artifacts that we need during pre-flight execution than the amount of memory required to store the entire segment trace.
I see. So pre-flight means I go over my 1 billion cycles, I mark a few checkpoints.
Yes.
And then it allows me to fill up traces from each checkpoint.
That's right.
Brilliant. Yeah.
And we can in that way also begin to parallelize our witness generation.
Okay. So are there any teams sort of using all these techniques that we've seen so far and implementing everything in one go?
Yeah, there are several really talented techniques that have achieved basically the unthinkable benchmark of having real-time proving for Ethereum blocks, meaning the ability to prove an Ethereum block execution in lower than the Ethereum slot time. So Succinct and SP1 have been able to do this. RISC-0 has been able to do this with their SNARK technology as well, using exactly this entire set of techniques of GPU programming, cluster level programming, fast witness generation with pre-flight execution, and achieve something really remarkable using many servers coordinated at once.
So I guess I'll keep prompting, like, can we do better? Like, can we be faster or get the same speed with fewer resources, like fewer servers?
Yeah, so what are the resources we care about at this point? We care about the latency of computation. I think if we tried to make that 10x smaller, we would run into new bottlenecks using this set of techniques, but also we start to care about the cost of computing this as well. Money's a resource, and we might care about the power required to produce a large SNARK computation. So really, the future of this industry is custom hardware. When it's a big enough problem in a big enough market, we can reduce the cost of producing many proofs by having dedicated chips that are optimized for these types of computational problems. So, like, where in the story does this fit in? This is essentially about going all the way back to the beginning, reducing the number of instruction cycles required to do the computation in the first place.
So these field multiplications that we have to do everywhere.
Yeah. Being able to do field multiplications with either fewer resources or in fewer instruction cycles or at a higher clock speed. And for that, we need to design new hardware. So let me erase this.
I guess this is analogous to how GPUs first came to be, right?
Exactly. I mean, if we think back to early graphics programming, it was a software engineering marvel to be able to produce stuff like Doom with regular CPUs. And then now we have rich graphics by developing custom hardware with with processing units that are adapted to that specific problem. So what does it take to actually do like a field operation in a CPU or a GPU? For a prime field, it looks like an integer multiplication with additional cycles to perform a modular reduction.
Right.
So one thing we could do is just make the native data type of our processing unit to be field element multiplications. We could even handle extension field multiplications using instructions instead of many cycles of different instructions. The other thing is when we look at NVIDIA GPUs and what they're optimized for, they are more limited than CPUs, but they still optimize for floating point arithmetic. And in fact, they often advertise the number of flops, floating point operations per second that they're able to do. They have flexible control flow.
So this is like if statements. And,
yeah. And they have a very flexible memory hierarchy, meaning your core can access any piece of data from global memory, and the network on that's routing data between the cores needs to be able to handle these.
So you're talking specifically about GPU cores, right?
I'm talking about GPU cores. Cool. That's right.
Just because the word core has been, used at every layer almost, and
global memory with like cache. So because if we wanted to design hardware that's specifically good for SNARK use cases, we can adapt them to the actual types of memory access patterns and the actual type of computation. So we might be able to get away with a memory model that's more limited than global memory. We also see this happening in the AI space, where you have experimentation with different types of memory models like systolic arrays that can be targeted for like these specific types of workloads. We may not need flexible control flow because we're basically doing streaming passes over data, and no one is really using floating point operations to do SNARK computations. We mostly care about integer arithmetic for prime fields,
right? And
then doing like bit level operations for masking in order to do reductions. So my company Irreducible basically investigates this problem and is designing custom hardware for SNARKs, and actually for a specific SNARK. So one thing that we learned early on is if you're going to design custom hardware, you should be very opinionated about what the protocol is so that you can adapt the hardware really well to that use case. So some of the things that we've learned is that there is a type of finite field that is very amenable to cryptography called binary fields that are extremely good in hardware. We talked in our last segment a bit about the cryptographic advantages of binary fields, but also there's hardware level advantages. So what are binary fields? They're a different type of mathematical object and so Baby Bear, which is what we began this session talking about, is an example of a prime field. So we can put this, for example. This is actually the set of integers modulo a 32-bit prime number. A binary field, there is a 32-bit binary field that systems like Binius use, and I'll just call this B32. There are different representations of binary fields, but we'll treat them all as one family for now. And one thing that we've learned in our investigations is that the hardware efficiency of doing 32-bit binary field multiplications versus 32-bit prime field multiplications, it's about 5x more efficient for a binary field multiplication.
So here we're saying the number of CPU instructions to do one field multiplication is smaller here than there.
Actually, no. It's more interesting than that.
Okay.
This is talking about if we write a digital logic circuit. So we're not talking about CPU cycles anymore. We're going to write a native Boolean digital logic circuit, which is going to get created with transistors and gates. That the number of gates required to perform this this computation within a certain at a certain clock speed is 5 times lower than this.
Okay. Then the number of gates at the same clock speed. Okay.
Yes.
Wow.
And like, is this a secret? Actually, no. This has been well understood in cryptography, and that's why binary fields show up in standards like AES and in various error correcting codes. So is this a pure win? Well, actually, we have found that it's really hard to take advantage of this on traditional CPU and GPU architectures. So GPUs have these, they have dedicated circuits inside of the cores. The GPU cores are just digital circuits that do integer multiplication.
Right.
They do not do binary field multiplication, and they don't have instructions that are particularly helpful for that. So even though at the native digital circuit level, binary fields have this advantage, when you're trying to use widely available hardware today, it's actually makes a lot of sense to stick with prime fields.
Okay.
However, if we're talking about the future of creating custom hardware for SNARKs, we think binary fields have these advantages. So what else can we do before we have these chips? There are devices called FPGAs.
Field Programmable Gate Array.
Field Programmable Gate Arrays. I'm not going to write that all out, but it's basically reconfigurable hardware.
So gate arrays is, as we can think, a bunch of gates, and we can choose what gate it is and how they're wired?
Yes.
Cool.
And you can actually
like
write the same sort of hardware description language, the same sort of hardware designs that you might go and send to a foundry and or a fab and get back an actual chip. You could instantiate these on an FPGA with some modifications.
Okay.
These devices are typically, or they're commonly used for prototyping in order to test out your circuit designs. But in special cases where consumer hardware doesn't do an operation that efficiently, you can actually run them in production and what we've seen is the field multiplication throughput of binary fields that we're able to achieve in an FPGA rivals the field multiplication throughput of consumer GPUs using prime fields, which is pretty remarkable that you have this hardware that's designed for a specific purpose and that reconfigurable hardware by choosing a different underlying mathematical object could compete with that.
I see. So if you ported that same design to an actual ASIC, you expect to see it to be faster than the GPU.
Yes, and like ultimately, why is this? When you put things into a chip, you get rid of the reconfigurability, you're able to produce an extremely power efficient and scalable design at the expense of it takes a while to validate this hardware design. It takes a while to get it back from a fab, and it's quite expensive. So I think when the space matures and stabilizes, we will end up with custom hardware to do these types of operations.
That makes sense.
So one thing you might ask is, like, am I talking about ASICs here? What is an ASIC? We've seen those in Bitcoin mining. They're application-specific integrated circuits. We actually probably want more flexibility than an ASIC. An ASIC is a specific circuit. We can get more flexibility by building something that's like a GPU architecture, but with an instruction set that's adapted to what we need.
Right.
So why is this more flexible? It means that we can write software that our custom processor is going to read in and do some type of configurable operation, but instead of configuring it at the circuit level, we're configuring it by making it a software programmable processor. Okay. I've heard these referred to as ASIPs, as application-specific instruction processors.
So can we think of it also as like a binary field processing unit? Like
we
a
could
BPU or
yes.
Yeah. Cool.
So that's one way that we could get the advantages of custom hardware with some flexibility.
That makes sense.
I think that's everything I have to say about high performance engineering for SNARKs.
Amazing.
today.
So we have parallelism. Eventually, we can't throw more machines because we're limited by memory. Then we have these pipelining ideas. And then we saw how to split up witness generation and how to split up even just the whole statement and make smaller proofs to be able to cluster level parallelism and then aggregate all this. And then custom hardware.
Exactly.
Cool. Thank you very much, Jim.
Thank you. This was a pleasure.